It's about quantum communication advantage in TFNP. Figure is the same. Right.
Hi, thanks for the introduction. Yeah, so I'm going to be talking about quantum communication advantage. You don't need to know what TFNP is to follow this talk. This is joint work with Mika Göös at EPFL, Tom Gore at Cambridge, and Jiawei at UT Austin, who's in the room. Great timing. So let's even recap what is communication complexity. Well, Alice and Bob receive some x and y, and they want to compute some, let's say, joint function on x and y. And we don't assume any computational bounds on them. All we care about is how many bits they need to communicate, or qubits. And why do we study it? We study it because this model is extremely expressive. It simulates circuits, it simulates streaming algorithms, property testing algorithms, and more. And at the same time, it's very tractable. We are able to prove unconditional lower bounds for problems that we care about. So a model to keep in mind in the classical case is this fully interactive randomized communication where they're allowed to exchange messages in any order they want, and they're allowed to use random bits to decide their message. And this is the strongest classical model that is studied in literature. And a very weak model to keep in mind is simultaneous message passing. This, on the other hand, restricts the amount of interaction that Alice and Bob can have. So they receive some x and y, and the only thing they're allowed to do is prepare a message based on a single message based on their input and send it to a referee. The referee then does some computation and outputs the answer. And this model is weaker than the model in which we allow one-way communication between, let's say, Alice to Bob, because Bob could always just pretend to be the referee to simulate an SMP protocol. So if I allow Alice and Bob to send qubits, this is the weakest quantum model of communication studied in literature, mainstream. So what is our result? Our result is that there is a search problem where it has an upper bound in the quantum SMP model, which is poly n. N here is not the size of input, but another parameter that I will control. So it's a search problem in the sense that Alice and Bob receive x and y, and they want to find a z such that x, y, z is in some fixed relation R. But for any classical protocol which is allowed to be two-way randomized, there is an exponential in n lower bound. Moreover, the search problem is a TFNP relation. What that means is that it is classically verifiable, and it's total, which means every possible input is valid. There is no promise on the input. So the motivation for studying this, one of the motivations at the very least, is quantum advantage. In particular, we would like to design an experiment that demonstrates unconditional quantum advantage, but we also wanted to have classically verifiable solutions. Another feature of our result is that quantum advantage results usually come in two flavors. Structured problems usually have a promise on their input, but like I said, our problem has no promise on the input, and it's can be considered an unstructured problem. And it's famously hard to get examples of unstructured quantum advantage. In fact, it's possible if you're in the setting of query complexity of total Boolean functions. So let me also show you how our work compares to previous quantum classical communication separations. And it's a very old field with a lot of work. I think in particular to compare would be the hidden matching problem, which is also an example of a classically verifiable problem which has quantum advantage. But there, the upper bound only holds in the one-way model, not SMP, and the lower bound also only holds in the one-way model and not the two-way model. And I also want to mention that our protocol will also not use any shared entanglement or even shared randomness. And Alice, Bob, and referee, all three parties can also be computationally efficient. They can be implemented in BQP. I think, for example, GRT22 was very focused on trying to get a computationally efficient protocol, and we matched the result in that way. So what's the problem? Told you all the implications. What's the problem that we care about? Well, the problem is going to be based on Yamakawa-Zandri's relation. This relation, which we call null code word, exhibited a average case quantum classical query separation, and is celebrated for that reason. Let me define it for you. So for the problem, you will fix a code, which is not going to be part of the input. And that code is going to be some subset of its alphabet to the n. And our input is going to be this h. So h has this nice representation of being written as a concatenation of a bunch of maps, h1 up to hn. And each hi just maps the alphabet of the code to 0 or 1. And what you want to do is, given an h, you want to find a code word such that on every single index, its symbol is mapped to 0. So you can think of this as asking to invert this function h on some code word c instead of an arbitrary input in the domain. So what Yamakawa and Zandri showed is that if your code is a certain folded Reed-Solomon code and h is a uniform random map, then this problem has linear quantum query complexity but exponential randomized query complexity, where n is the message length of the code. So to port this into the communication setting, we define bipartite null code word. What does this do? Well, the input was already defined in terms of these n mappings for every index. We're just going to give the first half of the mappings to Alice and the second half of the mappings to Bob. So Alice knows which of the symbols in the first half map to 0. And my claim is that this problem has an efficient SMP protocol. In fact, the state that Alice and Bob send is this product state of the phi i's. And each phi I just is a superposition of all the valid symbols which map to 0 on hi. Why does this work? Well, it works because the Yamakawa-Zandri algorithm is completely non-adaptive. It makes all its queries ahead of time and then prepares these states phi I, and then the rest of the circuit is does not touch the oracle at all. So Alice and Bob just prepare this state after making queries, and the referee does the rest of the circuit. So now on to the hard part. How do we prove a classical lower bound? Well, why do we even believe the lower bound to be true? I think the intuition comes in two parts. The first observation is that a fixed code word is very unlikely to be a solution. If you pick a uniform random h, then every code word is mapped to all zeros with probability 2 to the minus n. And morally, querying one code word should not reveal much information about many other code words, because a good code is pseudo-random. It looks like you sampled a random subset of alphabet sigma to the n of that size. So to prove the lower bound, we proceed in 3 steps. First, we define some very structured protocols called subcube protocols. This will allow us to directly prove a lower bound for the problem on those. The lower bound goes through formalizing this idea that a good code does not reveal much information about other code words, and it corresponds to a combinatorial notion of list recoverability. And we instantiate folded Reed-Solomon codes with slightly different parameters that we need to achieve the lower bound. And then the final step is to lift lower bounds for subcube protocols over the uniform distribution to arbitrary protocols. And this is building on a technique of Wang, Yang, and Zhang from, I guess, 2 years ago now, and who further build upon like lifting machinery for randomized query to communication lifting theorems. So let me define to you what subcube protocols are, because one takeaway of this talk is that if you want to prove lower bounds over the uniform distribution, all you have to do is prove lower bounds for subcube protocols. So subcube protocols require me to define what a subcube is, and I'm going to define it in slightly different notation than you might have seen. So I'll say that a subset of the hypercube is a subcube if there is an index set I such that if I truncate all the strings in X to be only have symbols from the index set I, then this is a singleton set. So what I'm saying is that X is constant at this index set. And if I look outside this index set, it contains all possible substrings. So it contains the hypercube of size not of I. And I'll say that a protocol is a subcube protocol if it has this property that, well, any communication protocol can be represented as a protocol tree, and each tree corresponds to a rectangle. If you haven't seen this, believe me, this is true. And the claim is that every rectangle of this protocol tree is basically a product of subcubes. So did I just redefine decision trees? Because this seems very close to just like querying things. Well, no. Here's an example where subcube protocols have logarithmic communication complexity. Alice receives an X, and she just sends the first index where her X is 1. This is a partition into n plus 1 subcubes, and it cannot be efficiently simulated by decision trees. It is true that if your messages were 2 array, in the sense that if you sent 1 bit at a time, then this is the same thing as a decision tree. But in general, it's more expressive. So I think I won't have too much time to go into the lower bound, but for now. So I'll talk about open questions. First open question: our candidate for this communication separation requires decoding of folded Reed-Solomon code in superposition. This isn't really possible on near-term devices, so it would be nice if we had a simpler candidate which had a more NISKI separation. From a theory point of view, it's very interesting to try to get separations for total Boolean functions. Like I mentioned, in the query setting, we know that this is not possible. At least we can't get exponential separations, or even separations more than a 4th power. And it's also interesting from a technical point of view to try to get lower bounds for number on forehead communication, where this is a setting where there are k parties and each party knows every input but the ith one, the one they are. So think of it as, you know, the party game where your card on your forehead. The issue with the latter two problems from a theory point of view is that for the first, we don't have any candidates for getting this total Boolean function separation. And for the second, we don't have any techniques which lower bound randomized communication without also lower bounding quantum communication. So that's it. That's all I had to say. Thanks for your attention. If there's interest, I can try to go through the lower bound of the subcube protocol. Is that a yes? Okay. It's number on forehead. It's like okay. I don't know what to believe, but I have certainly tried to prove that there's an exponential separation and failed. Yeah.
Sorry, not sure if I missed it, but I think, okay, so the construction is basically you kind of get the Yamakaw's Andre you transform that into a communication problem, right? But doesn't so then the challenge now is to change the complexity, the classical complexity lower bound for computation into a one for communication. Is that why you need to introduce the sub-Q protocol and everything?
Yes. So you need to be able to prove a lower bound in this really strong two-way randomized communication model, and this implies the lower bound for query complexity, which Yamaka was Andrew already proved, but it's stronger than that.
I see. Okay, thank you.